Okay, so I think it's time we can get going. So first of all, everybody, you're really welcome. Thanks for joining in our webinar today. So this is the first webinar that we're doing in our master series, and it's our webinar called Deep Learning Uncovered. So I'm really excited, first of all, to kick off our master series with this webinar, and also to invite Dr. Kevin McGuinness from DCU and James Conway from Mastercard to join us on the panel for the webinar. So in terms of the agenda, how today is going to run is that basically we're going to have about a 15-minute panel discussion. So this is where we have some questions, and we're going to basically just chat around what deep learning is, how it's being used, what are the challenges that companies are facing in using deep learning, and how it can be applied most successfully within organizations. So that's going to take about 15 minutes. Then Kevin's going to bring us through our tech session. So he's actually going to demo some deep learning processes in action. So I'm going to let him explain all of that when we get to that. So that's going to be pretty exciting. And then we'll come back for a Q&A session. So basically, if you look in your webinar box, there's a Q&A option. So as we're talking, please feel free to jot down questions that you have. And we have Krisolis HQ, so our very own Brian McNamee is on hand, and he's going to be curating the questions. So he's going to help us out in making sure that we have questions and good questions for people. So hopefully everybody can hear us. Hopefully you can all see us. And just first thing I'm going to do is just introduce ourselves. So I'm Aoife D'Arcy, I'm the CEO of Krisolis. And Krisolis basically is a boutique consultancy and training company based in Ireland. And we offer training consultancy services for companies across all things data, analytics, machine learning, and AI. And we have Dr. Kevin McGuinness, who will introduce himself in a second, from DCU. He is an assistant professor in the Department of Electronic Engineering, and he's also a member of the Insight Data Center for Analytics. And James Conway is the lead data scientist in Mastercard. So we're going to now get going with our panel discussion. So I'm going to stop sharing my screen, and hopefully now you can see myself, Kevin, and James. So first of all, I'm just going to ask Kevin and James to introduce yourselves. So Kevin, we might start with you. So maybe just introduce yourself and what you do in DCU.
Sure, thanks Aoife. So as you said, I'm an assistant professor in DCU, and I'm also with the Insight Center for Data Analytics. So in DCU, I teach machine learning, and I also do research in machine learning, and particularly in deep learning and computer vision models. So that's my main area of interest.
Cool, brilliant. And James, how about yourself?
Sure, yeah, so I'm James Conway. I'm the lead data scientist at Mastercard Labs, and that's part of a global R&D group. So what we do is we take projects and things from other areas of the business that might be considered risky, or that from where the areas they are, people might not have the resources or the time to commit to the projects, and specifically AI components, we would take on those and help them bring those through their entire life cycle. So, you know, start off with your analysis, you know, then do whatever learning you want, and then deployment, prototyping, and then eventually out to support.
Brilliant, super. So I suppose we might start off with a nice easy question to begin with. We might start with you, Kevin, and just explain to people, and particularly people who may be on this webinar who don't really know what deep learning is. So maybe a little explanation as to what deep learning is, and I suppose specifically, why is it different from standard machine learning?
Sure, yeah. So deep learning is kind of a type of machine learning. It's a branch of it, essentially. So deep learning is machine learning. It's not a totally different thing. It's just a particular type of it. And it's kind of characterized by using parametric predictors, so models with parameters that you need to figure out, just like many other models in machine learning, like linear regression and stuff like that. The difference generally is these parametric functions are often, you know, compositions of other parametric functions, so nested functions, right? And these are often referred to in the deep learning community as layers, right? So you have multiple layers of a network that are put together to form a big complicated function, which generally consists of stuff, some of the stuff that's linear and some stuff that's nonlinear. And then the other big difference then with standard machine learning models, and this kind of comes as a consequence of this layering and composition, is that the loss functions, or what you're trying to minimize when you're trying to fit a deep learning model, are non-convex. And the implication of this, non-convex just means it's not, you think of it roughly like it's not bowl shaped. And this essentially means that optimization, you're not going to find the global minimum that you would if you're solving a linear regression model or a logistic regression model. So you have to settle for some kind of local minimum or some place in the loss space that generalizes well. But it turns out that it doesn't really matter too much, because often the global minimum with big complicated models like this is way overfit, right? So just like in normal machine learning, we have to deal with problems with overfitting. So usually we don't really mind if we don't solve the optimization problem exactly, as long as we get something that generalizes as well. So that's what I see as the two big differences with many of the standard models that are used in standard machine learning.
Cool, brilliant. Thanks, Kevin. And I suppose, James, from your perspective, what types of problems are you using specifically deep learning for in Mastercard, or what applications have you seen it being used for?
Yeah, so right now we have a project where we're doing some image recognition. So it's at point of sale terminals. So if you have products without barcodes, would you be able to scan them and recognize what they are, and as an inventory management system? So we're working with primarily in emerging markets. So where they have kind of individual products, and where they might, if you have instead of getting a pack of nappies or diapers, they'll open it up and they'll sell individual ones. So how do you keep track of that kind of inventory stock? So we have an application now where it's working on mobile devices, where they can just scan through the various items that they might have, and it would work like your usual barcoding system in a shop. And that's kind of one application of computer vision that we're working with right now. That's looks like going to be quite successful.
Oh, cool. That's really interesting. And I suppose moving on from that, Kevin, I don't know if you have any thoughts on, I suppose a lot of people, and I suppose that's a really good example of how deep learning is used in that kind of image space. And not that it's a fault, but a lot of people will say, oh, it's just used for image and text. And that's what deep learning is used for. I suppose, do you agree with that, or would you see it being used in other areas as well?
No, I wouldn't agree with that completely. I think it's had a huge impact in the areas of image and text for sure, but it's much more broadly applicable. One of the reasons why images and text work so well, and this will kind of give you a hint as to things that might work very well with it, is that they have some sort of temporal or spatial structure, right? So the pixels aren't just coming at you in independent order, right? They go top to bottom, left to right, and an audio or a text document, it has some structure that words have meaning depending on their positions. But there's many other things that are similar to this. So you have things like audio, right, or any time series or anything like this. Anytime when you've got data that's like that, it can actually be exploited quite a lot in deep learning, because it means it's amenable to things like convolutions and various structures that people have come up with in deep learning, where it really cuts down on the number of parameters you need in a model. But that's not to say that's the only type of data that will work with these models, right? So any type of data, tabular and things like that, when there's a complex relationship between the thing you want to predict and the things that you want to use to make those predictions, then deep learning is often a good choice. So I think it does lend itself to many things just beyond images and text.
Yeah, cool. Thanks, Kevin. I suppose as a classical statistician, I'm particularly interested in the time series element. I think it'll be really interesting to see in that space how things evolve in kind of coming years and months and years. And I suppose, James, from a practical application, I suppose particularly sometimes people see kind of a lot coming from academia. And there's almost a kind of that never work in reality. What will happen when you try and apply this with the IT infrastructures that you have within organizations and businesses? So I suppose, do you see, what are the challenges that you've seen or you faced in using deep learning practically, and particularly in deploying deep learning models? Have you seen any particular challenges, and more importantly, how have you overcome them if you've come across them?
Yeah, and when I talk about that, image recognition one, it was an effort to get it running on mobile devices. So that's something that we worked on a lot. So reducing down the training time, so all the training is done, on the cloud, and then we deploy the models to mobile devices. But I think a lot of it as well is around the data sets that you capture as well. So when you're doing these things in academics, a lot of times your data is already curated for you. There can be a lot of times when you're doing practical examples of where you just get your pictures for your training set are just completely black, or there's a hand obscuring the part that you want, and that kind of thing. So there's a lot of kind of filtering and things that you want to do, and various things like that you want to do on your data sets that you want to be clear to. And yeah, just when you're deploying, then you need to have the good support team there as well, because for us anyway, data scientists typically want to work on the interesting things, then when they're done, hand it over and move on. But that's not always the case. You know what I mean? You still need people to kind of help your support team, to guide them through what you've done, what you've developed in the entire process on that, essentially. So yeah, you need to think of the whole life cycle when you're developing, and not just package it up, deploy it, and it's done.
Yeah, I always say, I completely agree. I always say, like, when we work with teams, like almost deploying a model, any model, it's almost like the beginning of the life of that model. It's a bit like sending your kid to school, and you have to kind of nurture it a little bit. So you do have to engage with both on the business side, people who are using it, and also that kind of making sure that the infrastructure is set up. And I suppose in terms of that, is there any specific frameworks that you use or technology that you're currently implementing to deploy?
Yeah, well, currently we've got a Kubernetes cluster that we're kind of working everything with Docker containers, which does make that handover transition quite easy. That you have everything is containerized and kind of standard within the containers, and then you can hand over those pods and across. But we have everything kind of running in our own lab infrastructure, so we're trying to help the wider organization, kind of guide them through that process as well, and get their own setup and that, and that maybe eventually transition to the cloud entirely. We don't know yet.
Cool, excellent, thanks for that. So I suppose on that note, having talked about technology, we might hand over to Kevin for a little while. So Kevin's going to bring us through. I'll let him explain what he's going to do, because I'm not going to pretend to be an expert in this, so I'm going to leave it to our expert. So Kevin, if you want to share your screen, and we'll hand over to you.
Sure. Let me just see now. Hold on just a second, because it's after, of course, jumping off onto my other desktop, and I don't know how to get it back onto this one.
Of course it has. Live webinar, it's not going to go right.
Yeah.
No, you're grand. Take your time.
Can I drag this over?
And one thing, while we're just waiting for Kevin to set up, do feel free to type in any questions that you have on the Q&A in terms of, is there anything specifically you want to know about deep learning or particular applications or technology? So it looked like, woohoo, we're in. So I'm going to hand you over to Kevin now and let him do
Can you see the browser here as well?
Yeah.
Yeah, okay, great. Thanks, Aoife. Sorry for the slight technical difficulties there. So what I'm going to do at the moment is sort of talk you through a little bit about how you might build an image retrieval engine using something that we call transfer learning. So if you've ever asked yourself the question, how does reverse image search work on Google? This will hopefully sort of take a step towards answering it. So if you're not familiar with reverse image search, that's the feature in Google where, instead of typing in a text query, what you do is you just upload an image or grab one from the internet and hit search. And when you do that, you're trying to find like images that look similar in some way or contain some semantics. And if you sit down for a while and start thinking about how you might actually implement this, you realize that it's actually not very straightforward, because what you really need is some distance function that will measure the similarity between two images. It's not quite so easy to come up with one of them. And the first things you sort of think about is like, oh, well, maybe we'll just match individual pixels. But then there's problems with, what if the images aren't the same size? or, you know, if you take two images and, you know, you mirror one left to right, you've changed every single pixel, but they're still the same thing, right? So you can spend some time thinking about this and you'll find it's quite difficult. One trick to do this is to use what's called transfer learning, and that's where, and this is a hugely valuable technique to know about in deep learning, because often you don't want to sort of attack a problem from scratch. You want to reuse a piece of the solution from another problem, and transfer learning is one way of doing that. And the idea here is what we do is we take a network, a deep neural network that we've trained on a different task. In this case, it's trained on a task called ImageNet, and then we sort of repurpose it for an image retrieval engine. And I'm going to talk you through how exactly we do that here. So as I'm going through this, I'm going to be kind of skipping over bits just in the interest of time. But this is the kind of thing that we could go into more in much more detail in a class setting. So the data set that I'm going to use here is called the Oxford Buildings data set. And it's got, you know, 5,000 or so images in it. So I'm just downloading it here. Some boilerplate is I'm using the framework called PyTorch here, which is one of my favorite deep learning frameworks. It's especially good for research because it's quite flexible, although TensorFlow tends to be a little bit better for deployment than PyTorch, but I'm using PyTorch here. So this is a typical pattern in PyTorch. We define a data set, right? It's just going to encapsulate how to load images from our Oxford data set, right? So it's quite simple. We need to just define two things, get item and a length, right? And this will get an individual item, and this will tell you how many things are in your data set. So on this part here, I'm just instantiating the data set, and you can see that we have 5,000 images, and the first image looks like this. So this is a data set that contains lots of buildings, basically, but then also a bunch of random other stuff. And these are from Oxford. It was developed by the Visual Geometry Group in Oxford University. Okay, so this is the data. So we haven't really done anything yet. So the next thing I'm going to do is a little bit of pre-processing of the data. This is very typical when you're doing things with deep learning. In particular, neural networks like their inputs to be sort of between roughly -1 and 1, you know, with sort of unit variance. So we kind of normalize them a little bit to make sure that the pixels don't range from like 0 to 255, but rather range from, you know, roughly -1 to 1, so they're zero centered. That just makes the networks a little bit easier to train. So if the networks was trained like this, when we're going to reuse it, we want it to be sort of similar thing. Okay, so here's the model that we're going to use. This model is called a ResNet 50. This picture here is actually a smaller version of it, but I couldn't fit the ResNet 50 on the screen because it's actually a 50-layer model. So when I was talking earlier about, you know, deep neural networks are compositions of functions, you can think of each one of these blocks as a function, and this whole thing is a big composite function. And these all have parameters in them that would have been sort of started off randomly set, but because we're reusing a pre-trained model, these have all been sort of fixed by training it for a different task. And the output at the end of this network, in this case, this small picture only has 10 dimensions of output, but the network that I'm using has 1,000 dimensions of output because it was trained on a task to classify images into 1,000 different classes. Now, for the purposes of retrieval, trying to find a similar image, we're not really interested in these 1,000 classes, right? What we are interested in is finding a representation of the input image that sort of, when you compute distances between them, they make more semantic sense. And one of the nice things about these networks is that when you train them, you go from things that are very low level, like pixels, up to semantics, which are very high level. And as you move through this network, things are getting more and more semantic and less about the detail of the image. So we expect the representations or the output of the function at somewhere around this point, right? If you just cut off this last part here, or cut off one of these earlier parts here, will be something that maybe the distances make sense a bit more. So here I create a ResNet. This is built in because it's a well-known model, and you know, move it onto my GPU. And it's another thing to mention is you usually need a GPU for doing a lot of the processing in deep learning because these models tend to be quite computationally intensive to train. So this is the model, and this is all the layers. You can see it's quite complicated, but it's actually the same structure, essentially repeated over and over again. And just to check that this is a pre-trained model, we can visualize the filters which are on the first layer, which I'll just point out here. So the first layer, this is what's called a convolution layer, which basically means we train these little filters on the image, and these are little 7x7 images, so we can look at them. And if it wasn't trained, these would be just random pixels, but you can see it's learned things like edge detectors and various different things on the image. I'm just going to skip over a few of these bits here because they're little sort of details. And the next part here, what we do is essentially run over our data set and turn our images into features, right? And by the end of this here, so for all of our 5,063 images, we're 2048, right? So we now, for each image, we have a 2048 dimensional representation of that image that we hope is sort of semantically meaningful. These are some standard tricks that we tend to do in retrieval engines, and one is, for example, reduce the dimensionality of this to something a little bit smaller and normalize it. But once all of this is done, we can query the data set. So here's an image from the data set. This is the index image 2. And to actually do a query, once we have this, because we've normalized our features here, in other words, we've projected them onto a unit sphere, it turns out that distances and similarities, or cosine similarities, are the same. And in fact, we can compute cosine similarities all in one step for our whole data set, given the query features and the features from all of the images in the data set, just using a matrix multiplication, which is what we have here. So a single matrix multiplication gives us scores for each of the images. And then we simply rank by the score, okay? One of the nice things about this type of approach is that this is completely parallelizable. And you can split your images across multiple machines. You can broadcast your query to these machines. And this is essentially how Google does this for billions of images. And you collect the results and you just merge the lists. So what does the results look like? Well, if we take this query here and we do our ranking, so we just sort by score, you can see what the top 10 look like. And you can see they're all pretty much the same thing. And you can also then look at the bottom 10 on this list to see what are the things that this representation thinks is most different from this building here. And you can see it's just kind of random stuff, right? People and things like that, not buildings anyway, right? And if I still have the file here, I'll see. No, I don't. I'm not connected. So Google Colab is really annoying because it just kicks you off if you're not paying attention to it, and then you have to start again. But sometimes it doesn't delete your file. So let me see. It hasn't. Good. Okay. Let me see if I can load in these features and we'll run a few queries. So where are my features here? I don't want to run through the whole notebook because it takes a little bit while to do this. Okay, so is this working? Yes. Okay, let's try a different query then. I don't know, any random number. Maybe something 50. No. Okay, so that's some building. Then we do the ranking, we do the sort. Let's see what the results look like. Okay, so you can see that it likes this sort of tower thing. So towers are seem to be what it's looking for here, steeples and things like that. And what doesn't look like a tower? Well, people, I guess, aren't towers. So, these are the things that it doesn't think are. And you can play with this, and this is essentially what kind of things like Google image search does. And I mean, you can enhance this a lot. This is just a basic demo, but this gives you the sort of picture of how this kind of thing works. So I know that was really fast that I went through that, but of course we're limited on time here, and I'd love to go in and explore all the details and let you much more detail and understand how this stuff really works.
Super. Thanks a million, Kevin. Thanks for that. I hope people find that really interesting. And I can see in our Q&A that there's a couple of questions. So I know I'm just going to open it up here. So one of the questions that we have here is from ML John. So I was wondering how practical it is to fine-tune hyperparameters in the real world for deep models, is one question.
Well, I think it's challenging, right? Because there are many hyperparameters to tune, including the entire architecture of your models, all the learning rates, batch sizes, the list goes on and on and on. It is practical if you've got a lot of computes to do random search on a lot of these things, and there is ways of doing model completely automated, sort of do a search of the architecture space and various different things. There are certain parameters that we know are more important than others. People build up good intuitions on how to do this. The good news is that there are many hyperparameter configurations that will give close to optimal performance, and it's not that hard to find them. So if you add an extra layer onto the model that I just created, and you train it on ImageNet and do all of that stuff, and again, you'll end up with a model that's going to give you roughly the same amount of accuracy. It's not going to be that different. You can actually sort of go in and change many of the hyperparameters of these models quite dramatically and see very little difference in how they perform. So the robustness to these hyperparameters is one of the features of deep learning, which means you don't necessarily have to go too far in your hyperparameter search. And in fact, I don't think we wouldn't have yet discovered how powerful these models could be if they were so sensitive to hyperparameters, because the chances of us randomly stumbling upon a hyperparameter configuration when it's only a small number of people investigating these models would have been very small. So essentially, because they were easy to find, we found them, and that means that you're not going to need to spend too much time doing hyperparameters, I think.
Yeah. James, if you want to add to that.
Yeah, I broadly agree. I mean, we pretty much do random search for hyperparameters in practice, when we're training like RLSTMs or LSTNets, and generally, we get pretty good results, from, let's say, training over like an evening or a weekend. We probably kick off the job as we're leaving and come back in the morning. But what I would say is to have in your head your critical values, what your acceptance rate for accuracy is before you keep tuning it. Otherwise, you'll get bogged down in the weeds of trying to get that extra 1 or 2% or even, 0.1%, because when you're working with large numbers, it could represent a lot of value, but the amount of effort involved getting it might not be representative for it.
Great, and there's some other good questions coming in. So by the way, if anybody else has questions, please feel free to add them. So Rena's asked, just Kevin, for you to go over again what you do to the pre-trained model to make it usable for your data.
Yeah, so what you do is you have this sort of big, long model that's composition of loads of functions, and the input of it is an image, and the output of it is one of these 1,000 classes. So it's a vector of length 1,000, right? And there's going to be something's going to be close to 1 if it thinks it's that item, right? So if this is the item that corresponds to a cat, and you put in a cat image, you would expect a 1 to come out in the cat position and zeros nearly everywhere else. But of course, for retrieval, we don't really care exactly what it is. We're just looking at things that we want to put similar things together. So you just basically take a virtual scissors and you cut off the last layer, right, the 1,000 layer one, and you're left with the layer before that, which has got a lot of semantic information, right, but isn't the exact semantics of the outputs, right? So in this new space, all the cats are going to be close together in this sort of the output of the layer beforehand, and all the cars are going to be close together, and things that are semantically meaningful are going to be clustered together in this layer, because that's what makes it easier to turn that via one single transformation into the 1,000 classes at the end. So the key step here is chopping off the last layer, right? And there's various ways of doing that in the code or in implementing it, but you want to get the output from, you want the input to be the image, go all the way through the network, but not through the very last bit, and then take the representation for that. That's what you use for your task. That's what you're going to use the images.
Cool, great. Hopefully that answered your question, Rena. And one other question here from John. So in their experiments, they had used transfer learning for anomaly detection. And specifically, they'd used ResNet 18. However, they didn't find it worked. And the reason for this is that they think that ResNet 18 is trained for a multi-class classifier type, whereas anomaly detection is essentially a one-class classification type. So would you agree with that? And I suppose the other thing is, I'd add to that is there anything you'd recommend, that could be used for anomaly detection, or that you've seen useful for anomaly detection?
So anomaly detection is a very hard one. The reason is often that anomalies are by definition infrequent, so we don't have very many examples of them, and they don't all look the same either, right? They can be very different, and particularly in vision, you can have all sorts of different anomalies. And so it's very hard to test these models and get training data for these models. So assuming the approach that was taken here was we will take images, we'll extract features using ResNet 18, and then we will keep features from normal events and fit some model to that. Maybe that's a Gaussian or a mixture of Gaussians, or maybe it's just the nearest neighbors. And that sometimes works, but it may not work that well because anomalies are not really related to the high level semantics of the cloud you're looking. You might use features from lower level layers. I think sometimes going to help because maybe the anomaly that you're looking for is more low level, or maybe you just need more examples of what normal things are to see what's anomalous. It's very difficult to say because there are many difficulties in the anomaly detection task.
Yeah, brilliant. Thanks. I don't know, James, if you want to add to that.
I just be careful when you're looking at anomalies of what you might think is an anomaly might actually just be part of your data set, and you might be causing bias or whatever by excluding these. Sometimes these are things that you actually have to train for as part of your model, and you might be just overfitting if you do remove them, if that's part of what you're trying to do.
Yeah, anomaly detection is one of my favorite subjects, and I've done a lot of work in kind of fraud detection. And what tends in, I suppose, a lot of the processes that I'd work with and teams I'd work with is there's an end point where you check that something is an anomaly when you find it.
Mm-hmm.
And I suppose the whole idea, a lot of deep learning processes, is that you don't have that. So I think it is a really interesting example and problem. But if you solve it, there's lots of great solutions out there, or problems out there that need solutions. So it's great. We have a couple of more questions. So do you see a move to productionized solutions based on deep learning? So things like image recognition tools and things like this. So
yeah, I would. Yeah, like I said, we have image recognition software. We're able to deploy it on tensor boards, and hopefully soon on Raspberry Pi, and very small scale machines that will allow people to you probably do your training online and then deploy the models over the network. But yeah, we have some commercial availability for that, and like our one application on the point of sales, I think, is definitely a good use case for it.
Cool, Kevin. I don't know if you have anything to add to that.
Yeah, I mean, there's already lots of APIs out there. Paper used to do things like vision and image recognition and things like that. So I know Google have a cloud vision one. There's a big push, obviously, at the moment, though, because it's expensive to do this stuff sort of centralized. But there's a big push to get this stuff on the edge. So to be able to do, if you want to do anomaly detection for CCTV, right? Maybe you want to alert somebody when somebody enters a region at a particular time, or maybe something more sophisticated. You don't want to transmit all your CCTV up to the cloud, process it all there, because you might have 1,000 cameras and they might be producing 30 frames per second. And even if your algorithm is real time, the amount you're going to spend on cloud processing to do that is going to be intense. So if you can get that processing over onto the camera itself, right, and you can get your deep models that are pre-trained, deployable on the camera at the edge, you can actually do this stuff much better. So I see a big push moving towards that at the moment as well.
Yeah, I was talking to somebody recently who's working in the robotic space, and one of the things that they're actually concentrating on is, they think that the models are there like to train, but actually deploying it in the robot, so as it doesn't need that actually the hardware would support it within the robot, and they're actually they see it as a hardware problem, as opposed to a machine learning problem that they're going to kind of work on kind of making more sophisticated hardware, which was really interesting. And I'm just going through some of the other questions here. So actually, this is a question that I had in my list of questions to ask. So somebody else has asked it. So I'd like to say great minds and all of that. So their team is thinking about using deep learning, but they've not done it before. So what would be your top tips for people starting to use it? And I'm going to interject here, apart from attending the deep learning masterclass, that's at the end of the month with Kevin. But apart from that, guys, do you have any top tips?
Yeah, I think, yeah, understanding your data and understanding the whole life cycle of your project. You know, do you plan to self-support this, or do you plan to transition this out to a support team? And who is that team? What does that look like? What training does that team require to be able to support this? All those things need to be taken into consideration. And even the end users, you know, are you improving their life? You know, is this going to be easy for them, or are they going to require some training? Because a lot of these things, people about who the end user is, and you know what their benefit from it. So it might benefit your company, but the end users need to be kind of on board with that whole process as well. You know, if you're making their life more difficult through your process, you have to explain to them why, and if it's making it easier, hopefully it should be a lot easier for them. And but just whatever training is required needs to be kind of considered as well as part of the whole process.
Great, thanks James. And Kevin, I don't know if you want to add to that.
Yeah, so first thing I would say is related to what the transfer learning is. If you can, don't start from scratch. Start from something that somebody else has done and adapted to your problem. In particular, you know, using pre-trained architectures and models and fine-tuning them for your problem, adapting them, fine-tuning them for your problem is very, very effective. And it's very effective, especially when you haven't got much data. And it's also even effective when your domain is completely different to what the models were originally trained on. In fact, we've used pre-trained models from ImageNet and fine-tuned them for medical image computer-aided diagnosis, and had some success with that. So I think that's one thing. Another would be, you know, deep learning is just machine learning, right? So just remember all your machine learning training and practice good data hygiene and things like that. I mean, you can make just the same mistakes as you would make with other type of machine learning. If you're coming from a standard statistical machine learning background, one of the things that you will have a strong prior to do is let's choose the smallest model that fits our data, right? And when it comes to deep learning, you actually probably want to take the opposite attitude. You want to take a model that overfit your data and then regularize it back again to make it. And that's how you tend to get the best performance out of these things, which is completely against the intuition of many people who've been trained in classical statistical machine learning. And in terms of regularization, I'd say data augmentation is your friend, right? So data augmentation is one of the most effective regularizers there is out there. And the idea there is, for example, in images, you know, if you got an image, you can get another image by flipping it left and right, or you can take lots of little crops of the image, you can jitter the colors, and all of these things preserve semantics, but they give you a new training example, and you can massively increase the amount of data that you have by doing this kind of technique. So they'd be tips that I would think are important.
Brilliant. Top tip of the day, go large. Go big with it. Brilliant. Well, I'm going to finish up with one very quick last question for Kevin and James. So just in terms of use of deep learning, what is the most interesting example that you've seen? So maybe James, if we start with you.
So I'm quite you know, intrigued by these new deep fakes that they're doing and how that's going to be. I don't know if interesting or rather scary is the example, you know, but yeah. And I really like the applications of deep learning in medical imaging technology, you know, where it's outperforming the some doctors, you know, in diagnosing cancers and things like that, tumors. So I think that's a really strong application, and you know, will benefit society as a whole, I think.
Great, thanks James. And Kevin?
Yeah, I agree with James there. They're both very interesting applications. Another one that's related that I think is really nice, I've always quite liked, is the idea of generative adversarial networks. So these are GANs, as they're known, and you can use them to generate novel content. But the idea behind them is super cool, right? Because, you know, typically in the past, when we're trying to define a neural network or for a task wheel, we have to come up with a loss function that makes sense, right? And the loss function that you want for generating images, what is that? Like, it's like, how do you write down the loss function for it looks like an image, right? It's difficult to do. And then the idea behind again is, well, maybe we can't write that down, but maybe we can train something to do that too. And if we train the two of them at the same time, they'll sort of reach an equilibrium. And then by the end of it, you can generate these amazing looking images of people, of cats, as always, you always generate cats and various different things like that. So that's really cool. And I think the concept behind, like, generating images is a little bit of a novelty or whatever, but the concept of what you're doing there, I think, has much broader applications. So that's one to watch for sure. And another one that I think is cool is, you know, these giant language models people have been doing, like GPT-2 that was released by OpenAI. Really fascinating that you can generate text that's basically coherent, that makes sense, and could even people from just a big language model, right? So
yeah. Brilliant. Super. Well, thanks, guys, for that. So I'm just going to say, first of all, thanks to the guys, and just finish up the webinar. So I'm, you know, conscious of time, and I know three of us could probably sit here and chat for about another 45 minutes, happily. But just in terms of finishing up, I'm just going to go through my last few slides. So as I said before, this is the first in a series of webinars and workshops that we're running. So our master's class, so this was the first. So this is the deep learning webinar, and the follow-up masterclass of this has been run at the end of this month. So if you're interested in what Kevin was talking about and want to learn more about that, contact us to join our masterclass for that. And we're also doing a series of these. So each topic will have a free webinar like this, and then followed up by a masterclass where you can actually learn in depth all of the different techniques that are used for the particular area. So we're doing it in network analysis with Derek Green, conversational interfaces with Robert Ross. Our very own Brian McNamee is doing some semi-supervised learning, and we've allowed him to do some reinforcement learning just because he really wants to do it. So if you're interested in any of those topics or want to talk to us about any of that, please feel free. In terms of the follow-up from this, you will get a feedback form from us, and I'd really love if you filled it in. I know it'll take a few minutes, but we'd really appreciate it because all feedback is always very welcome. Krisolis. Also, anybody who's attended the webinar is going to get a discount code, 5% discount code for the Deep Learning Uncovered Master Series. So again, if this topic interests you more, you want to find out more about it, please contact us. And if you do want more information, you can get more information on our website, krisolis.ie, or info@krisolis.ie will also get you some information. So last but not least, I want to say thank you. So a huge shout out and thanks to Kevin and James. Thank you so much. I hope you enjoyed it. And also to everybody who joined today. So I know we are in very uncertain times and it's all a bit difficult, and different people have lots of different challenges. So thank you so much for joining today. We really appreciate it, and hopefully it gave you a little bit of a break from talking about self-isolation and coronavirus and lockdown. So thanks a million to everybody. Thanks guys, and hopefully we'll see you again for the next webinar in a few weeks time, which will be on network analysis. So chat to us all soon.